Yep. Hi, everybody, and thank you, Soki and Chris, for the introduction and for organizing this wonderful workshop. I'm sort of thrilled to see there are 136 people already in the audience. I don't think I have given a Exciton talk like to such a large audience, so I think maybe the Zoom format is one way that even after the pandemic we should use. So anyway, so I actually tweaked my title a little bit today to include some of the new results and some unpublished results. And I really wanted to have this as a discussion on kind of like, our understanding on exciton transport, how do we measure it, how we control it. And I would like to discuss with you today some of our recent effort in this regard. So to start, I want to show some inspirations has always been thinking about why photosynthetic systems are doing so well in terms of moving these excitation energies from these antennas to reaction centers. And in particular, we have been interested in this problem from the point of view that when you have these very, very closely packed chromophores, and which is a universal feature in all these antennas, how do you think about the energy transfer mechanisms, right? So in the sort of more well-known Forster picture, you think about this incoherent transfer from one molecule to the other, but in a system like photosynthetic antenna is strong intermolecular coupling, they can be stronger than say vibrational coupling, and also coupling to the environment, so on, so that you actually have these excitons that are delocalized over many molecules. And so that, how do you think about energy transfer in these kind of situations? So in particular, so Snuggy, if you could just give me like a warning, like 5 minutes or something, because I won't be able to read the chat when I'm giving the talk. So if you can do that, that would be appreciated. So anyway, so how do we think about how this sort of delocalized state, how do they move, energy move in between this delocalized state, is one of the questions that we have been interested in for a while. And so, and the other part of this equation is that how do you actually measure exciton transport, right? Because in sort of the more conventional way, people have been using like quenching or other exciton annihilation, other indirect way of thinking, measuring exciton transport, but then you miss the important time domain information that would allow you to resolve mechanisms. So, because for instance, if you think about like these transfer out this delocalized state, and if they are coherent, they're only going to be last for very short amount of time, like only orders of 100 femtosecond or even shorter. So you certainly need a very high temporal resolution. And in order to really measure transport, you would also want to have spatial resolution, right? So you want to be able to see how these excitation energy are moving around. One of our dream experiment always been like, well, it can be excite the antenna and watch how this energy move around the antenna and reach finally to the reaction center, right? So then you also need spatial resolution. So in our group, we've been using this method and called pumpable microscopy or transient absorption microscopy, and to develop that for exciton transport. And there are multiple ways of doing this. In our cases, I assume like many of you will be somewhat familiar with transient absorption spectroscopy. So like, you have a pump that excites this molecule to excited state and have a probe like probing the response of the excited state. So in a microscopic format, you will couple it to a microscope. So there are a couple ways that you can do this and to get spatial resolution. One is to do bin scanning. So you can scan both the Bowman probe bins, or you can scan a sample to construct images. And in a measurement, when you want to do transport measurement, you want to be able to localize one little bin and scan the other bin relative to each other. So a lot of times in our experiment, we localize the pump. So the pump is exciting certain area of your sample, and then the probe is scanned in space and to really watch how the energy migrate. You can also have a delocalized probe. So your pump is focused, but your probe is not focused. So it's a wide field probe, and you can image the whole wide field with a camera. So you probably hear from Naomi later in the talk about some of those methods. And so this is a very active area. So there are many groups working on this, combining some sort of spectroscopy with microscopy. And I would say this is an incomplete list, and I'm really also thrilled to see that there are many more people working in this type of area to really combine time and spatial resolutions. So in practice, then, kind of what it looks like in the lab is like, so here it's a video showing that the pump beam is in the middle, right? So you can focus onto a certain area, and then the probe beam is scanning around. So you can imagine that to detect a pump probe signal away from where you actually pump, you would have to have some kind of excitation energy transport from where you pump to where you probe. And in terms of image contrast, to probe an exciton signal, in our lab, we either use like some kind of ground state bleach. So this is a transient absorption spectrum out of one of the PDI molecules that I will talk about later, that you can also either look at the bleach of the, this is the S0 to S1, the ground state transition. So you can either looking at the bleach signal, or you can using some kind of excited state absorption signal to as an image contrast of your exciton population, right? So in our experiment, then what we do is we can use the pump to excite the excitons, and the probe wavelength will be tuned to some of these transitions, and then we scan this beam around to construct images. So one of our earlier work is a collaboration with Jasper Knuster, whom I actually see in the audience list. So hi, Jasper. Anyway, so this motivation for this earlier work was to use this porphyrin tubular aggregates as a analog for photosynthetic system. That we can first really understand very well these exciton structures, and then to image the transport of these excitons. And with Jasper, then we model the absorption spectrum of this aggregate. It turned out like they rolled up into like a tube, and so it's almost like an antenna for this green sulfur bacteria. And so for these porphyrin aggregates, then you have two excitonic transition. One is the lower exciton energy exciton, Q band exciton, and then the other is the B band exciton. And since this is published, so I'm going to go through it relatively quickly. So if you have a question, you can ask in the end. So then with the calculation, we have come to a conclusion that for the Q band exciton, the exciton on average is delocalized over 200 molecules. And you say, well, that's a really large number, but it has something to do with the geometry of these aggregates. And you can think of this aggregate as stacks of rings, and each of rings have about 43 molecules. So this is about 5 rings. And also one thing to keep in mind is that this is the average number. So the exciton band have many states in it. So the lower state, the lower energy states, those are the ones that are more important for transport. Those are actually more localized. They are roughly delocalized over 10 molecules. So then we can do our transient absorption image. And first we have the pump and probe overlaps and to scan the sample so that we can actually find where these tubular aggregates are. So you can see a very well correlation with the atomic force microscope image with the transient absorption microscopy image. And we can then pick up one of these aggregates, so we can localize our pump onto one of these aggregates and then scan the probe, right? So, and then the probe polarization then is aligned to the long axis of this porphyrin aggregates. So then we can get images of, by scanning the pump and probe as a function of, by scanning the probe as relative to the pump and taking this image at different time, you can then get images as shown here. So in this porphyrin aggregates, the oops, I lost my, okay. In these porphyrin aggregates, the external lifetime is relatively short, so it will only go out to like tens of picoseconds. And what we do is we can take a slice on this along the axis of these porphyrin tubes, and we can build up the external population along one axis. And this is along the long axis of these tubular aggregates. And we can see that even though they look quite similar, but actually the width of these Gaussians are different from have expanded from 0 picosecond to 15 picosecond. And this is because the extons have migrated in this 15 picosecond of time. And we can if we assume that the external motion is all diffusive, then you would expect that all this can be described like a random walk of extons, so that the diffusion constant can be extracted by looking at the difference of the width of this Gaussian. So if you plot the variance of Gaussian as a function of time, and the slope of it will give us twice of the exton diffusion constant. So then from this way, we can extract the exton diffusion constant to be around 6 times centimeters square per second. And which is actually quite remarkable, because this is much higher than things like, you know, a rare disorder polymer like P3HT, which will be 3 orders of magnitude lower. And as I mentioned in the previous slide, that these extons that are actually important for transport, they are you know, not that delocalized. They are delocalizing over maybe 10 molecules also. So so that means that, you know, by really thinking about how to organize these molecules and induce these interactions between them, that you gain a lot in modulating this external migration. And with Yasuo, we also did simulating the kind of the lower bound of the exton diffusion constant without taking into effect like this exton being delocalized. And the theoretical lower bound is 1 centimeter square per second. So this is still higher than that prediction, meaning that the delocalization does play a role. So in that initial example, we were somewhat limited by two things. One is that the exton is still kind of the ones that are important are still relatively localized. And two is that there are not a lot of ways that we can change the interaction in those kind of tubular aggregates. So in a more recent work, recent collaboration that we started with Jasper, Frank, Spano, and also Ro Tempora. And I see Frank also in the audience. So if you have any question for the theory, you can ask them. Anyway, so we started to work on this group of molecules that are quite popular for organic electronics. These are pairing diamides. And the pairing diamides, we were interested in them because they are much more tunable, in that you can change this interaction by changing the structure of it. And in particular, we look at two different aggregates, and one is one that based on this called N-phenyl PDI, and there's tetraphenyl PDI. The difference is that the substitution groups, either on the this edge or on this what is known as the bay location, they can induce different amount of slip stacking. And so like it's in a way of changing, they can be significantly impact the short range coupling, which known as the charge transfer, also known as the charge transfer coupling. So I think I might actually skip this slide and get to this charge transfer coupling, because the kind of coupling that we are maybe more familiar with are this long range Coulombic coupling. And charge transfer coupling is the Coulombic coupling, of course, is based on dipole interaction. The charge transfer coupling is relying more on the orbital overlaps, so that it's much more sensitive when you change your molecule configuration or intermolecular distance just even a little bit, it can have much more larger effect. So Frank, of course, is the expert in this kind of theory, and his earlier work predicts that for this type of pairing diamide molecules, you can see the charge transfer coupling can change from like a J type to an H type by even just slightly change in the short X slip and the long X slip. So you can see that the charge transfer coupling JCT in here can go from blue, which is H-like, to red, like which is J-like, by changing the molecule's structure just by a couple of angstrom also. So we were with Franklin, we were able to pick out, actually was by luck, two of these PDI molecule. One resides the long range coupling for both of aggregates are H-like, but the J and the short range are both are J-like, but by different amount. And so so in one sense, we can look at this type of HJ aggregates, and by changing the amount of the short range coupling, we can essentially tune these exciton band curvature. And the band curvature is related to the delocalization of the exciton, right? So the larger curvature of this band, then the more delocalized of these excitons are. So, so since both of these aggregates are these HJ, so you will see that it will go from this, for the Coulombic only, you have this blue curvature down here, looks like a front face, and then by the J, different amount of this charge transfer J coupling, you can push it down, right? So you can push it down by different amounts. So in this case, you can actually push it from a H type aggregate to a J type aggregate. And for the two molecules that we looked at, the N-phenyl aggregate, it would be the J coupling is not strong enough to push it all the way down to J. So it was still more or less like an H aggregate. And interestingly, for the tetrophenyl aggregate, the H and J almost cancel out entirely. So it's like a no aggregate. So then you would have a situation that for the no aggregate, these excitons are quite localized. They almost like they are just on the individual dimers. So you have series of dimers versus a aggregate that this exciton is still delocalized. So we would expect that the exciton would be more coherent in the N-phenyl aggregates versus the tetrophenyl aggregates. And we also did some modeling of our temperature-dependent PL spectrum and to figure out the amount of this charge transfer and Coulombic coupling in this two aggregate. And so then we went ahead and imaged the exciton transport in this two aggregates. And as you see that, these are the image similar to what I showed before. And since I'm almost out of time, that I'm gonna cut to the chase. So indeed, we do see quite a bit of difference between these two different aggregates, especially at a very early time. So kind of before 10 picosecond also, the N-phenyl aggregates, which have a more delocalized excitons, has a very high diffusion constant around 10 centimeters square per second, versus the tetrophenyl is around 2. So indeed, this kind of strategy seems to work. And the part that I don't have time to talk about is that you will see that this, in both aggregates, at longer time, it becomes slow, quite slow. It slowed down by around tenths of picosecond. And so we are thinking that this has something to do with, like, in this group of molecules, like excimer formation and so on, are quite prevalent, so that you can, you would have to, you have exciton trapping, like by those type of states. So in the last 2 minutes, maybe I guess, or 1 minute, is that I just want to kind of give a future direction that we're working on. So what about if we can use, like, say, a strong line matter interaction to even enhance this coherence much, much further, right? Much further than what is even possible in things like a photosynthetic system. So recent work has shown that by coupling to cavity and by forming this very delocalized polariton state, you can, in theory, get to coherent lengths that, on microns or much, much longer. And so in the very recent work that we've done with, in collaboration with Theodore's group, we have started to use this this kind of strategy and use silver nanoparticle array as a cavity to induce these very delocalized polariton states. And the initial research we did is on excitons with two-dimensional perovskite quantum wells, but this can also be used for molecular system. And I just want to quickly show that in our initial work, indeed, we show that when we have these excitons coupled to this array, which is, you can think of as an open cavity, and you can see much more rapid and long-range exciton transport. We have also some evidence in molecular aggregate excitons, but I'm running out of time. So so I'm just gonna end pretty much here. I'm gonna end pretty much here that with leaving the outlook for you to really like thinking about how do we actually measure and control exciton transport in molecular system, and how do we overcome things like disorder or localization. Anyway, so here's the people who actually did the work, and I highlight the student who actually did most of the work, Tongzhu, Suat, and Lin Rui, and I thank you for your attention.